Log on, tune in, find out. Another good idea from Cambridge.
Announce our next talk at this Portuguese conference, and this will be Colin Guillarmou, and he will speak about inverse boundary problems for systems in 2 dimensions.
Thank you very much. Okay. Well, as usual, thanks to the speaker for invitation in Cambridge in this conference of a specialist in inverse problems. Louder? Is it switched?
It doesn't help. It's only for
Okay. So, yeah, I thank the organizer for inviting me to talk in this conference. So I'm going to talk about some joint work with. Actually, it's a series of work. It's a series of work. First with Leo 2, and the last work on inverse problem for the systems is also with Leo 2 and Pierre Albin and Normale. And well, we consider some elliptic first order or second order system for domains of C, or more generally Riemann surfaces with boundary. And essentially we use the new approach of Buchheim of constructing complex geometrical optics with a phase which has a critical point. So maybe first I should just give the theorem we are proving. Let me start here. So the first case is consider M equipped with the metric is fixed. It's a Riemann surface. With boundary. So G is fixed, and really, in fact, you just need the complex structure to be fixed, so or the conformal class. So G is fixed, or more general. I mean, we can reduce, in fact, to the conformal class or complex structure fixed. The surface can have topology on several ends if you like. So on such a surface, in particular, you have the complex structure and a d-bar operator. And we consider first the first order system, the following first order system. So we consider this. So it's a system like this. And with a zero order term, which I will denote maybe A minus and A plus. 1 and 2 equals 0. So d bar is just a d bar operator associated to the complex structure on a complex complex vector bundle. Let's say of rank n. So I will denote it E. So E really, you may think of it as Cn over the manifold, but when you have Riemann surface, it's not necessarily Cn. So E, in fact,
Well, it's not necessarily trivial.
no, it's trivial. In fact, there is a general result which says that on an open Riemann surface, I mean surface with boundary, any complex vector boundary can be trivialized. So in fact, this is diffeomorphic if you want. And here, U1 or section of the bundle and U2, because you know, of course, on a surface in general, d bar will map, let's say, C infinity section on the bundle to C infinity section of the bundle, but with value in 0 and form, maybe T star. So you go from a function to forms in general. Of course, in the domain of C, it's just function to function. But so U2 are sections of E tensorized with T01 star. And the star here is this is with respect to G. Okay. And A plus, A minus, and Q are just potentials, if you want. So matrices value potential or endomorphism. So this guy maybe here, I call it V. V is an endomorphism of the bundle. So it's really a matrix. So for the regularity, we will assume the following. So we assume that Q plus or minus are in W1P, and P is bigger than 2. And for A, okay, we have a kind of bizarre condition that in some certain space, which is in CR of M intersect with WSP, or SQ of M. So these are the usual Sobolev space with one derivative in LP. And there are some conditions on RSP, so typically R plus A. It's just a technical thing, if you like. Or sorry. So there are some conditions like this, and S times Q is bigger than twice N plus 1. So I don't know, maybe it's not optimal, but this is what we get. So the Cauchy data, oh, maybe this guy will call it D, like a Dirac operator. Its square is a Laplacian. And C of D plus V is just the Cauchy data. And it's just defined as the boundary value of U1 and U2 on the boundary. If you want, where U is a solution. So the result we can show is the following. So this is this was proved with these are 4 people, including me. So we show that if the Cauchy data of D plus V1 is the same as the Cauchy data of D plus V2, then there exists F and G, some isomorphism if you want, isomorphism such that, so maybe there's C1. Yeah, there's C1. Such that their boundary value is the identity on the surface, the first thing, and the following hold. So D plus V2 is simply a certain sort of conjugation. D plus V1. So this is really as operators. D minus 1, 0, 0. So this is what we can get. And somehow is the best you can do. It's gauge equivalent. If you want, this is really a gauge. So this is really an equivalence. So this is the first thing. And we can apply this for the Young-Mills operator or connection Laplacian. There's an application of this. Okay, the same authors. So if with the same assumption as before, if you consider a connection nabla, maybe I will write it like this: D plus X. So X is a connection one form. Is a connection on the bundle E as before, which is isomorphic to M times Cn. You can consider the Laplacian L, let me call it Lj. Oh, and maybe nabla J here. So these are two connections. And you consider the connection Laplacian, which is just the following. So it's also called the magnetic Laplacian, I think, in the literature. And you add a potential, so Vj, or just endomorphism, of E. The associated Cauchy data is defined a bit like before. So this, these are the restriction of this thing to the boundary. So nu is the normal to the boundary. Normal derivative. So it's just the derivative for the connection, but normal. And you assume that U is a solution of the equation. So this is the Cauchy data for this problem. If the Cauchy data agree, maybe I'm going to use everything. So if C of L1 equals C of L2, then we get the following. So there exists F isomorphism of E, which is a C1 in regularity, such that I didn't say about the assumption on the regularity. So it's a bit similar as before. This guy has to be in W1P for P bigger than 2, and X has to be in this bizarre space here. So as you can see, the regularity depends also on the rank of the bundle, at least in what we do, such that F is the identity on the boundary. That's the first thing. F is unitary Oh, I didn't say the connection here is supposed to be unitary. Two connection, unitary. So this means this is anti-self adjoint. This connection one form. And V1 equal F minus 1 V2F, and the connection nabla 1 equal F minus 1 nabla 2F. So this is again the gauge equivalence for the connection Laplacian. So I should say actually this thing we proved before with Leo Tzu for line bundle, so just the usual magnetic Laplacian. So here it's a generalization for systems. And actually for the line bundle case, it was quite interesting because somehow if you look at the usual literature on the magnetic Laplacian for the inverse problem, the thing you can do is recover the curvature of the connection. So the curvature of the connection for line bundle is just dx, where x is this connection one form. And once you have the curvature, in general you work on a simply connected domain, you can integrate in a way. So you recover whatever you like. But if you're on a Riemann surface, you cannot do this. So you need to recover the monodromy of x once you know the curvature. So we have a proof which is for line bundle quite interesting that Leo found actually. To recover the integral of the flux really of the curvature along all closed trajectory or closed all loops by sort of unique continuation argument. But this works only for line bundle, doesn't really work for the general case. And then, as I will explain, there's another method to actually recover directly the gauge. So there's sort of two proof, and at least for line bundle, two proof. Okay, so that's what I want to say for the statement. So I think in 2 dimensions, okay, I don't want to talk about the literature in higher dimension. There are many results. In 2 dimensions, I think this was known for the line case, for just the single equation, under certain assumption maybe under assumption that the v and x are small, and as you will see, this new approach of Buchheim actually allow to sort of do everything. So let me explain the idea. So first I will explain, because it's pretty neat idea, the method of constructing CGO with a phase which has critical point. So I have 45 minutes, right? So let me remind maybe the method of Buchheim. And in fact, I will also give an alternative idea, which is in the paper of Immanuilov. Ullmann Yamamoto, which is pretty similar, but use the Kalman estimate instead. Of course, in this paper they do the partial data, which is more general. So the way, as you know, the way you recover a lower order term for inverse problem is, at least as far as I know, the only method at the present time is to construct complex geometrical optics, or FADF type exponential solution. And in 3 dimension, people were using linear weight, and in 2 dimensions this failed. And the idea of Buchan was to use nonlinear weight. So it's based on nonlinear weight for Kalman estimate. So essentially you want to, let me explain, I explain for just the simplest case first, Laplace plus potential. So you want to construct solution to construct some exponentially growing solution of this form. So they depend on a small parameter which I will call h, like in the semi-classical literature. So there is a phase which is complex, an amplitude, and a remainder. And h is going to 0. So phi is the weight, it's complex. And of course, I mean, it has better be the case that the exponential of the phase times the amplitude solve the free equation. And Laplacian kill, of course, harmonic function, so in particular holomorphic and anti-holomorphic. So one of the ideas of Buchan was to use the holomorphic function, and a particular one which is nonlinear, which has a critical point at a given fixed point that you want to recover the potential. So at the end, well, sorry, I mean, from Cauchy data knowledge, you get this. You get that the integral of the difference of potential against the product of the two solutions. So let me call this like this. Sorry. Like this. Okay, sorry. Maybe I want to say this will be U1 and UH2, so the solution for the first potential and the solution for second potential. I want to use the same but conjugate, because if this guy is holomorphic, the conjugate will be anti-holomorphic and would also be killed by Laplacian. Or 1H and or 2H, like this. And maybe with a minus would not change so much. And what I know from Cauchy data is this, the integral inside, right? So if you plug this solution and if you assume that phi has critical point and d bar phi is 0, so critical point at z0, non-degenerate, here non-degenerate, so the Hessian is non-zero, or the second derivative non-zero at z0. You get actually here from this thing that the difference of potential against maybe twice or minus twice, it's not very important, the imaginary part of phi over h plus remainder in terms of h. So of course you expect this to be small. This will goes to 0 as h goes to 0, hopefully, if you construct a good CG1 equals 0. And from this, if this is let's say small enough, you apply a stationary phase. This you can, let's say you can construct the phase so that it has a unique critical point at z0. Then this is equal by just usual stationary phase to the difference of potential at z0 and time h. Maybe you can assume also that phi vanish at z0 so that you don't have oscillation. Plus remainder. So if the remainder is small enough, you get that 0 is equal to this and you're done. So in the paper of Buchan, the phase which was used, it was for the disk or for domain in C. The phase which was used was z minus z0 square, which is of course the simplest one you can think of satisfying these conditions. So phi of z is just complex component was the following, just that means 0 square. So now the question is how to construct this CGO. And if you already tried to construct a complex geometrical optic, you know that having a phase which vanish at a point or more submanifold is not a very good thing for estimates. So the way you can think of the construction is maybe by applying first, let's say, prove a Kalman estimate. So a Kalman estimate, in this case, you can actually show the following. Maybe plus v. Doesn't change so much. In L2, plus constant time gradient of u. So this is the Kalman estimate you can show in this case. And you see that here there is a little loss compared to the usual Kalman estimate you will get, for instance, for linear weight. Or in general, you will get 1 over h. And the loss is due to the fact that there is a critical point and is unavoidable. Maybe this is not completely sharp, but at least you cannot get 1 over h. So once you have the Kalman estimate by usual functional analytic method, you can invert, if you want, the adjoint of this operator. So this implies that for any f, let's say in L2, there exists u in L2, in H2 actually, such that this operator applied to u, equal f, and in addition you get an estimate on u. So u is essentially the inverse of this, because you get a lower estimate here. C square root of h times f. Okay, just by Laxmirgram. So this means if you apply exponential phi over h a to this operator, the error will be Vj times exponential phi over h a. Once you conjugate with the weight, you have to invert v times a for this new operator here. So this would mean that this guy is actually O of square root of h by this Kalman estimate, right? Now square root of h, if you come back here, you see that the stationary phase gives you an h, so it's not good enough for the remainder, because the square root of h time a which is square root of h. But still, you can solve away a bit more. You can find the next term in the expansion here. So it's quite easy. I mean, quite easy, not really easy, but it's not so bad. And the idea is as follows. So, want to improve the ansatz exponential phi over h times a by adding a term times a plus, let's say, R1, so that the error is smaller than, let's say, h, power of h. So for this, you just look at the equation. exponential phi over h Laplacian exponential, sorry, minus phi over h plus phi over h plus v applied to okay, so what you want is that R1 of h is equal to the error you have for the first ansatz, which is just Vj times A with a minus so that it cancels out. This is the next term in the expansion you want to solve. And somehow you have to invert this. So the very good thing of harmonic function is the following thing. So Laplacian is dz. How do I want to do that? So delta, yeah, dz bar dz exponential phi over h, exponential minus phi over h, right? Now this is holomorphic, so you can commute it here. Dz exponential phi over h, right? And this is, now you can put a minus phi bar here and plus phi bar here, because phi bar commute with dz. You're left with dz bar times an oscillating term, I psi over h, and psi is just the imaginary part of phi. Okay. So now it looks pretty good. I just want to solve this, maybe plus error, but let's say little o of some, maybe h or something. H would be enough, because then if I invert this error with the Kalman estimate, I would get h power 3/2, which would be much lower than this. So I want to solve this. I can, for instance, set R1 of h to be minus Vja dz bar minus 1. So it's just the inverse of this guy applied to this. It's just the Cauchy integral kernel, if you want, or any inverse of dz bar. There are plenty. And then I invert this. Sorry, this one. So it's just exponential minus I psi over h dz minus 1 exponential I psi over h. But this looks pretty good. So let's forget 1 second that psi has a critical point. This thing, semi-classically, let's assume that this is smooth also, to simplify. This thing is a semi-classical Lagrangian distribution. So it's an, if you want to, it oscillates on a Lagrangian defined by psi. So the Lagrangian is simply the graph of d psi, right? So the semi-classical wavefront set is contained in the graph of d psi. The Lagrangian is just m d psi m in the cotangent bundle. Now you act with a pseudo differential operator for the minus 1. If psi will not vanish, will never vanish, in frequency this will be supported outside the 0 section. So applying a classical pseudo differential operator for the minus 1 to such a semi-classical Lagrangian is actually like applying a semi-classical operator. So you gain 1 power of h. So applying dz minus 1 to semi-classical Lagrangian will give you h, because this is of order minus 1, time an expansion in power of h. And then you have an oscillating part. So you see you will get 1 power of h plus an oscillation. And playing with this, this will be actually enough. So in fact, here it's at the border, because The problem is the psi doesn't vanish, so you have to be much more careful. And you need estimates. So essentially you need some estimate. You can prove that this operator has a map from W1P, sorry, as a map, dz minus 1, as a map from LQ, maybe L2, to W1P is of this form. So it's not really H, and this is because of the critical points. So the way you prove it, you have to sort of use the usual stationary phase as if it was there were no critical point outside the critical point, and near the critical point you micro-localize very close, and you just evaluate the volume, and you see more or less you optimize, and you get this. It's a little bit tricky actually. So the way Buchheim prove it is by integral kernel method, and this is kind of sharp. So once you have this, this will tell you that this is O of H 1/2 plus epsilon, which is not completely enough, but in fact, if you look carefully, the term with A hitting this guy, you see that you okay, no, doing like this, I would need here. I mean, here, if you want, I can also remove the value of this guy at the critical point. And it turns out that when you do this, when you apply to a function which vanishes at the critical point, this is actually of order H, and you gain something. And of course, removing this doesn't change anything, because when you reapply your dz bar, it's a constant, so it's killed. So essentially, this is the way. There are a little bit of technical thing, but this is the way it's proved. And the Kalman estimate, also you can actually get it just from this factorization. It's very easy, in fact. You just use the Poincare inequality for the dz bar operator. So you don't gain any power of H, of course. And the other guy is just dz I dz psi over H plus dz. And if you apply to a function u, you can assume that u is real valued, for instance, so it doesn't change anything for the Kalman estimate. So if u is real valued, so I'm talking about the Kalman estimate now, just to give a short idea. If you compute this, you get this, plus dz psi over H u square. And it turns out that the cross product, by integrating by part and the fact that psi is harmonic, is in fact 0. So you get this. And of course, this is, this means you gain 1 over H to the price that you have to multiply by the derivative of psi, with vanish to first order at the critical point. And now from this, you can in fact prove, it's a little exercise, that this is, you can trade, if you want 1 power of H, by removing this and using this. CH, because I take the square. So this is a little exercise. So this is the way somehow you can prove the Kalman estimate. So now let me finish by saying how we use all these ideas for system. So for system, the problem Kalman estimate, maybe it's possible to do it, but it's not necessarily the simplest way. So we can use really the method, the way really that Buchheim wrote in his paper, which is more like integral kernel approach. But really it's an equivalent way. So now our result. So the way so let me do it for this operator d plus big V, where d was d bar star. right? So the first thing is to write it like this. Maybe I want to okay, maybe a minus. I will write it this way maybe, and q minus. And the first reduction we do is to consider this really as a d-bar operator. So this we can prove, even on a Riemann surface it works, that there exists a certain isomorphism Fa which satisfies that Fa minus 1 d bar Fa equals d bar plus A minus. And the same for this guy. So doing this, then we have a factorization. So d plus v is equal to okay, let me take the note so that I don't write mistake. It's Fa so plus star 0 0 Fa minus 1. Where is that? Minus 1. D plus, let's call V tilde. I will write what is V tilde. And here is Fa plus, so minus 0 0 and Fa star. Where is that? Fa plus star minus 1. So you can factorize this way, and V tilde is the following thing. V tilde is a new potential, which is just F. Okay, A prime was A plus. Yeah, I changed my notation. Star minus 1. So it's a new potential which is a conjugation of this one. A minus 0 0, and here a similar thing. Fa minus Q minus Fa plus star. Right. So you can reduce to, if you want, to the case where the potential is diagonal. Right? Of course, I'm cheating a bit here, because when I do this, I need to know something about this gauge. If I want to say my problem have the same Cauchy data, if I want to reduce to this new potential and say that the new problem have the same Cauchy data, this means that I need to prove that this gauge for the two problem, I mean for the first potential and the second potential, agree on the boundary. So this is very important. I need Fa1 A plus 1 equal Fa plus 2 on the boundary, and similar for Fa minus. So this is one important thing. And if I want to apply the method of Buchheim, of course, here I told you I need an exponential, I need a holomorphic function with a critical point at a given point, which is also Morse, non-degenerate, holomorphic. And on a Riemann surface, a priori, it's not so clear. I mean, you cannot take z minus z0 square. So we have a method using Riemann-Rohr and transversality argument, which say that there is a full measure set of points on the surface, so that there exists a holomorphic Morse function with a critical point there, and non-degenerate Morse. So by a sort of general argument. So for the phase we can do it. Can get it essentially by Riemann-Rohr, which give you some. It constructs some holomorphic function and a transversality argument. Riemann-Rohr will give you a holomorphic function with critical point where you like. The problem is there would not be Morse a priori. So you have to perturbate a little bit so that they become Morse. And this is where transversality is used. So I need this, and then I'm reduced to the diagonal case. So the diagonal case, we have like 2 minutes. Three minutes. So the diagonal case, let me just say a little word about how do the diagonal case. So it's really you can observe that this is what Buchanan did actually for the single equation. You can observe that this operator D is actually it commutes with this operator minus phi bar, exponential phi over h, minus phi over h, D. Just from the form of the operator D. So then if you conjugate this and this, I mean multiply by this, you're left with D plus VH, and VH is actually given by Q plus exponential 2i psi over h, where psi is the imaginary part of phi, and Q minus is maybe minus psi over h. Sorry? Yes, that's the tilde in my notation. Thanks. Of course, a Q tilde also, which is this new Q there. And now I apply, I want to construct a CGO, so I apply to, for instance, A and B are holomorphic. I apply to, if you want, I search a solution of this form, A, B bar plus or H, SH equals 0. So D kill this guy if A and B are holomorphic. So I'm left to solve essentially D plus VH times RH SH to be the remainder, which is VH times AB. VH times AB. The trick is to multiply by D, an inverse of D. You multiply by D minus 1 on the left. You're left with 1 plus D minus 1 VH equal time RH SH equal D minus 1 VHB AB. And it turns out that this guy, in a way, you write the equation and you see that this guy, if you want, is small in terms of h. And then you do a Neumann series, you invert, and this constructs you directly the CGO. And from the CGO, you recover this Q plus Q minus. Then there is the last thing I want to say is how to prove that the gauges are the same. And just one word, to prove they are the same, the trick is to, instead of constructing one solution with phi and the other one with minus phi bar to get an oscillation, you construct one solution with exponential phi over h, A plus remainder, let's say U1, and the second one with the opposite phase, maybe B bar, B, or I don't know. So there is no oscillation anymore. You let h goes to 0. You find a certain equation involving, because here, of course, there is the gauge coming. You find a certain equation involving the gauge. You do integration by part, and you use Hodge theory. Hodge theory tells you that something is the boundary value of a holomorphic function if and only if when you integrate against one form which is holomorphic, it's 0. And by choosing this A and B holomorphic, you actually get that FA1, FA2 minus 1, integrating against, on the boundary, integrating against holomorphic one form is 0. And this proves that this guy is the boundary value of a holomorphic function, which means that you can modify one of those so that you get identity. Modified by a holomorphic function, the appropriate one. And then you can choose the gauge to be the same on the boundary. Again, I'm stopping here because I'm over time.
Questions? Okay, then thank you very much, and that's for today's session.